the last class, we studied the update procedure which forms an integral part of the adaptive Huffman code. In today's class, we will have a look at two more components of this adaptive Huffman code, and these are encoding procedure and decoding procedure. Let us first have a look at the encoding procedure. Initially, the tree at both the encoder and decoder consists of a single node which we call as the not yet transmitted node known as NYT node, and the number of this node is the maximum number, that is 2m minus 1, where m is the size of the alphabet. Now, the code word for the very first symbol that we encode is going to be a previously agreed upon fixed code word. After the very first symbol, whenever we have to encode a symbol that is being transmitted for the first time, we send the code for the NYT node followed by the previously agreed upon fixed code for that symbol. The code for the NYT node is obtained by traversing the tree from the root to the NYT node. This procedure alerts the receiver to the fact that the symbol whose code follows does not as yet have a node in the Huffman tree. If a symbol to be encoded has a corresponding node in the tree, then the code for that symbol is generated by traversing the tree from the root node to the leaf or the external node corresponding to that symbol. So, the algorithm for the encoding procedure would be as follows. First, you start, then after you have transmitted the first symbol, the code word for which will be from the NYT list. For the second symbol, you follow the procedure as follows: read in symbol, then if this symbol is the first appearance of the symbol, then you alert the receiver by sending the code for NYT node. So, send code word for NYT node followed by the index for that symbol in the NYT list. After this step, we are supposed to update the tree at the encoder So, we will jump to a step which involves the updating procedure. So, let us, if this condition is not true, that means if the first, it is not the first appearance of the symbol, then else code word for that symbol is the path from the root node to the corresponding node for that symbol, and then again you call the update procedure. So, we have this step number 4 which calls update procedure, which we studied in the last class. Then find out if this is the last symbol. If it is the last symbol to be encoded, then we stop, else we read another symbol. So, we jump to step number 2. This would be the pseudo code for the encoding procedure. Let us try to understand this pseudo code in a much better fashion with the help of the example. Let us take the same example which we considered for the update procedure. So, let us assume that we are encoding a source consisting of 26 small case letters of English alphabets. So, in our case m is equal to 26. So, to find out the fixed code, we find out this E and R values, which turn out to be 4 and R is equal to 10. Let us take, we want to encode this sequence. So, the first symbol which we want to transmit is A. Now, as A is the first letter of the alphabet, K is equal to 1, and as 1 is less than 20, A is encoded as the 5-bit binary representation of K minus 1, that is 0. So, A will be encoded as 0 and the code word for that would be as given here. After you have done this, the Huffman tree is updated as shown in the figure here. So, we start with NYT equal to 51, and then after encoding A NYT 50, this node breaks up into two nodes. One is NYT new node and another is a node corresponding to A. As A has occurred for the first time the weight corresponding to element A is now 1 and the old NYT weight is also incremented to 1. Now, the next symbol to be transmitted or encoded is again A. Now, as A is available in this tree, therefore, the code word for encoding A or for transmitting A would be obtained by simply traversing the tree from the root node to the external node corresponding to A in order to find the code word. In this case, this traversal consists of a single right branch, therefore, the Huffman code for the symbol A is 1. So, for the next A we transmit or encode it as 1. Now, the third symbol to be transmitted is R. As this is the first appearance of the symbol, we send the code for the NYT node followed by the previously arranged binary representation for R. Now, if we traverse the tree from the root node to the NYT node, we get a code 0 for the NYT node. The letter R is the 18th in the alphabet, so K is equal to 18. Now, since K is less than 2R, that is 20, the binary representation of R is in terms of 5 bits. So, we represent R as binary representation of K minus 1, that is equal to 17, and that is equal to 1001. Therefore, the code word for the symbol R becomes 01001. This is the code word for the NYT symbol. So, the tree is again updated at the end of encoding R, and the tree becomes as shown here. We had looked in detail the construction of the update procedure in the last class. Now, the next symbol or letter to be transmitted is letter D, and the code word for the NYT, since D is occurring for the first time, the code word for the NYT node is obtained again by traversing this tree from root to the NYT node. So, if we traverse from the root to the node corresponding to NYT, we get the code word as 00. So, for D, the NYT node code word would be 00, and since D is the fourth letter in the alphabet and is less than 20, we represent it by K minus 1, that is equal to 3, and the code word for that is 0011. Therefore, the total code word for D would be NYT code word followed by the code word for the D. So, this will be the code word for transmitting D. The next letter to be encoded is V. Since V is appearing for the first time, we have to send the code word for the NYT node followed by the pre-decided code word for V. So, the code word for the NYT node would be given by the tree structure here, because this is a tree structure which is existing at the end of encoding D. So, the NYT code word would be 0 0 0. So, we have the code word for V as NYT code word 0 0 0 followed by the pre-decided code word for V. Now, since V is the 22nd alphabet, so K is equal to 22, which is larger than 20. So, we encode this as 22 minus 10 minus 1, that is equal to 11. So, we represent V by the 4-bit representation of 11, and that is 1011. So, the code word for V would be 000 followed by 1011, and at the end of encoding we again call the update procedure, and when we call the update procedure, the final tree structure is as shown here. Now, the next alphabet to be, the next letter to be transmitted is A. Now, if you look at this tree structure, then A has already occurred. So, the code word for the letter A in this tree is given by traversing from the root to the leaf node corresponding to A, and in this case it would be 0. So, the code word for the letter A would be 0. So, if we concatenated all these binary digits, we will get the code for this sequence AARDVA. Now, after having looked at the encoding procedure, let us look at the decoding procedure. So, at the end of encoding procedure, after we have encoded A, the updated tree would look as follows. We have just incremented the weight corresponding to the node A. So, now let us look at the decoding procedure. Now, as we read in the received binary string, we traverse the tree in a manner identical to that used in the encoding procedure. Let us try to understanding decoding procedure with the help of a flow chart. So, we start the decoding procedure by starting from the root of the tree. We keep on reading the binary bit string till we reach a leaf. Now, we check for the status of this leaf. If the leaf is a NYT node, then we read in E number of bits, that is 4 in our example, and check for the value of those 4 bits. So, if 2 raised to E turns out to be less than R, then if it is true, then you read one more bit to get 5 bits, and then you decode the element. But if the value is not less than R, then you decode by adding to that value of corresponding to 4-bit k plus 1, and then decode the element. After you have decoded the element, call the update procedure. If the leaf is not the NYT node, then decode the element corresponding to that leaf and then again call the update procedure. Now check if this is the last bit in the string of the transmitted sequence. If it is the last bit, you stop, otherwise you go back to the root and start reading the bit. Now let us try to look at this decoding procedure with the help of an example. So let us say that we have the same binary string which we had considered earlier. Let us assume that we receive this binary string. Initially, the decoder tree consists only of the NYT node. Therefore, the first symbol to be decoded must be obtained from the NYT list. So we read in the first 4 bits. This is 0, 0, 0, 0, as the value of E in our case is 4. The 4 bits 0, 0, 0, 0 correspond to the decimal value of 0. As this is less than the value of R, which is 10, we read in one more bit for the entire code of 0, 0, 0, 0, 0. Now adding 1 to the decimal value corresponding to this binary string, we get the index of the received symbol as 1. Now this is the index for A, therefore the first letter is decoded as A. The tree is now updated as shown here. So you update the tree at the decoder as shown here. This updating procedure is exactly the same the updating procedure which we have at the encoder end. The next bit in the string is 1. Now this traces a path from the root node to the external node corresponding to A. So we decode the symbol A and then update the tree as shown here. In this case, the update consists only of incrementing the weight of the external node corresponding to A. The next bit is a 0, which traces a path from the root to the NYT node. So the next 4 bits are 1, 0, 0, 0, which correspond to decimal number 8, which is less than 10. So we read in one more bit to get the 5-bit word as 1, 0, 0, 0, 1. The decimal equivalent of this 5-bit the decimal equivalent of this 5-bit 1 is 18, which is the index of R. So we have here A, R. We decode the symbol R and then update the tree as shown here. The next 2 bits are 0 0, again trace a path to the NYT node. So, we read the next 4 bits, that is 0 0 0 1. Since this corresponds to decimal number 1 which is less than 10, we read another bit to get the 5 bit word as 0 0 0 1 1. To get the index of the received signal in the symbol in the NYT list, we add 1 to the decimal value of this 5 bit word. The value of the index is 4, which corresponds to the symbol D. Continuing in this fashion, we decode the sequence 0 0 0 1 0 1 1 as V, and finally this as A. So, after having studied both adaptive and non-adaptive Huffman coding procedure, let us look at some of the examples of applications where Huffman coding is applied. One such example is for lossless image compression. A simple application of Huffman coding to image compression would be to generate a Huffman code for the set of values that any pixel may take. For monochrome images, this set usually consists of integer values from 0 to 255. In one such experiment, 4 images were taken and each image was of size 256 by 256 pixels, with each pixel taking values from 0 to 255. So, they are represented by 8 bit. This corresponds to 65,536 bytes. And on these 4 images, Huffman coding procedure was applied directly on pixel values, and the results of that experiment is as shown here. So, 4 images, let us call them as A, B, C, D, were chosen, and Huffman code was directly applied on the pixel values, and the result of that investigation is tabulated here. So, for the image A, after the Huffman code was applied, bits per pixel turned out to be 7.01, for B it was 7.49, and C and D is as given here. The total size in bytes are also indicated here. Now, the compression ratio has been shown here. The compression ratio is defined as the number of bytes in the uncompressed representation divided by the number of bytes in the compressed representation. The number of bytes in the compressed representation also includes the number of bytes needed to store the Huffman code. So, from this investigation, it appears that we got the best results for the image C. Now, this is always the case. The compression ratio is dependent upon the type of the images which are considered. Now, to get a better compression ratio, it is necessary to utilize the statistics existing between the pixels in an image. Now, in most of the images, neighboring pixels are highly correlated. What this implies that the value of the current pixel can be predicted or estimated from the values of the neighboring pixels. So, one of the simplest crude model which can be used to estimate the current value of the pixel would be to say that estimation of the current value is equal to the past value. Now, so instead of encoding the pixel value xn, if we encode the residual between the pixel value and its estimate, using this model we would get as xn minus 1. So, this would be the residual value which we will obtain after taking the difference between the neighboring pixels. Now, if you take this difference values and use the Huffman code on the residuals, then we get the results as shown here. The same images were considered, but now the bits per pixel representation of this is given here, and the compression ratios are again indicated out here. So, if we follow this procedure, then it shows that for the image A we get the best result. Now, both these experiments were conducted by constructing the Huffman code based on two pass procedure. In the first pass, the statistics of the symbols in the source, that is 0 to 255 integer values, was collected, and in the next pass it was used to code the same values. Now, if we had to use the adaptive Huffman coding procedure, then the results are as shown here. This results is basically obtained after applying adaptive Huffman codes on pixel difference values, and we see that there is a further improvement for the image A. Adaptive Huffman coder can be used as an online or real time coder. However, it is vulnerable to errors and also is more difficult to implement. We will have a look at better strategies for exploiting the statistical relationships between the pixel in the images. Just now we have used the simplest model of utilizing this statistical relationship in the form of estimation of the current value by the past neighboring pixel. Another application of Huffman code is to text compression. So, for text compression, application, it seems that Huffman coding is a natural form of coding procedure. In text, we have a discrete alphabet that in a given class has relatively stationary probabilities. For example, the probability model for a particular English novel will not differ significantly from the probability model for another English novel. Similarly, the probability model for a set of C programs is not going to be much different than the probability model for a different set of C programs. Now, simplest way to obtain the probability models is by counting the frequency of occurrence of letters in a document pertaining to a certain application, for example English novel. In an experiment, a document consisting of 70,000 bytes was Huffman coded, and the result was represented by 43,000 bytes. There is a substantial drop in file size. While this reduction in file size is useful, a better compression can be obtained if we first remove the structure existing in the form of correlation between the symbols in the file. Unfortunately, this correlation is not amenable to simple numerical models as it is in the case of image files. However, there are other somewhat more complex techniques that can be used to remove the correlation in text file. These techniques are based on what is known as dictionary concept. There are two types of dictionary. One is a stationary dictionary and other is adaptive dictionary. Let us consider only one example of a static dictionary. So, we will use dictionary concept for the encoding of the text material. So, a very reasonable approach to encode such source is to keep a list or dictionary of frequently occurring patterns. When these patterns appear in the source output, they are encoded with a reference to the dictionary. If the pattern does not appear in the dictionary, then it can be encoded using some other less efficient method. In effect, we are splitting the input into two classes. One class consists of frequently occurring patterns, and other class consists of infrequently occurring patterns. For this technique to be effective, the class of frequently occurring patterns and hence the size of the dictionary must be much smaller than the number of all possible patterns. As I said, the dictionary can be of two types, static and adaptive. Choosing a static dictionary is most appropriate when considerable prior knowledge about the source is available. A static dictionary technique that is less specific to a single application is known as diagram coding. In this form of coding, the dictionary consists of all letters of the source alphabet followed by as many pairs of letters called diagrams as can be accommodated by the dictionary. For example, suppose we were to construct a dictionary of size 256 for diagram coding of all printable ASCII characters. Then the first 95 entries of the dictionary would be the 95 printable ASCII characters. The remaining 161 entries would be the most frequently used pairs of characters. The diagram encoder works as follows. It first reads a 2-character input and searches the dictionary to see if this input exists in the dictionary. If it does, the corresponding index is encoded and transmitted. If it does not, the first character of the pair is encoded. The second character in the pair then becomes the first character of the next diagram. The encoder reads another character to complete the diagram, and such procedure is repeated. So, let us take an example. Suppose I have a source consisting of 5 letters A, B, C, D and R. Now, based on the knowledge about the source, we build the dictionary shown in the table here. Let us assume, so the dictionary is built as follows: all the letters of the source alphabet are included in the dictionary. So, all A, B, C, D, R are included, and then we have provision for including 3 more letters in this dictionary if we want the size of the dictionary to be represented by 3 bits. So, if we want the size to be of 8, then we have provision to take care of 3 most frequently occurring pairs. So, let us assume, based on some knowledge about the source, we find that AB, AC and AD occur very frequently. So, if we form a dictionary based on this, then if we have to encode a sequence, let us say A, B, R, A, C, A, D, A, B, R, A. Then the procedure is as follows. First we read the 2 characters, they form a diagram. Now check for this in the code, whether the code word exists for this diagram AB. Now if you look in the code which we have designed here based on some knowledge, we find that the code word for the diagram AB exists, and that is 101. So we code AB as 101. The next diagram is RA. Now if we look for RA, we find that RA is not existing in the code. So we take the first character of this diagram R and code it individually, and the code word for R based on this code is 100. So we code this as 100. The second character or the second letter in this diagram forms the first character of the diagram to follow. So we read in the second letter and form another diagram, that is AC. AC, the code word for AC exists in our code, that is 110. So we code this as 110. The next diagram is AD, for which the code exists as 111. For AB, again it exists as 101. For this it does not exist, so we code this as 100. Now only A is left out, so we code it as 000. So this would be the sequence of the code word being generated based on the concepts discussed. Now most adaptive dictionary based techniques are based on a very popular algorithm that is known as Lempel-Ziv-Welch LZW algorithm. This algorithm is well explained in the literature. We will not go into the details as far as this class is concerned. The idea behind this algorithm is that it dynamically constructs a dictionary from pattern observed in the source output. Dictionary based algorithms can be used to compress all kinds of data. However, care should be taken with their use. For if otherwise we may end up with data expansion instead of data compression. So, the advantages of the dictionary based techniques can be summarized as shown here. This approach is most useful when structural constraints restrict the frequency occurring patterns to a small subset of all possible patterns. These techniques are very efficient for text and computer type of communication, but it is not very efficient for the images. So, now we have looked into quite a few number of techniques for coding. We have seen that the Huffman codes is the optimal or compact code. Huffman code is a variable length coding approach. Now, there is another popular variable length coding approach which is known as arithmetic coding. Arithmetic coding is very useful whenever you have source alphabet of small sizes and when the probability of occurrence of the letters in that alphabet are skewed. That means they are not uniform. In such cases, Huffman coding procedures do not give very good results. So, in the next class we will have a look at arithmetic coding. But before we study arithmetic coding, we will study a simplified version of arithmetic coding, and that is based on what is known as Shannon-Fano-Elias coding.